just for the sake of presenting, I'll be showing some examples while I'm presenting. So I won't really be going over the slide in the present mode, because tapping out between the simulator and examples and stuff will be relatively, I guess, not as fluent when I do it that way. So I'll be continue the presentation in this particular state. Yes, there are spoilers if you want to look at the left, but anyway, yeah. Charles, just let me know when you think we should start.
Probably just wait until 3:20, like a minute, and then you can start.
Yeah.
Charles, the coolant is flowing.
Oh, really? Okay, wait. Maybe I'll go hop in general mode or something.
Well, Charles, I guess, is away. It's around 20, so let's get started. Yeah? Okay. So let's get started. So for today's tech talk, we'll be talking about occupancy grid. My name is Justin Kai. I'm currently the tech lead that manages the occupancy grid team with the 4 other members, perhaps one more, Wanda, who is not really our member, but work really closely with our project. So she's basically working with us right now. Today's will be mainly go over a bit of a, first we go over why and how occupancy, and then we're gonna work on what do we do with occupancy in our own stack. So let's get started. So what is mapping? Mapping, by definition, is a process of determining the environment relative to the known location. So let's say you're driving a vehicle. How do you determine the world around you? Let's say you see a tree, you see a light pole. How do you denote that in a certain data structure or certain methods that will allow you to quickly understand the world you live in? And that's why occupancy grid is born. Occupancy grid is a probability map of static obstacle in the environment. Its goal is basically to achieve mapping on observing, like having a correct and efficient data structure or data representation that we can keep track of all the static obstacles in the environment. The map contains a finite number of cells. Think of it as like a 2D array. Although realistically, it's not really a 2D array, but you can think of it as like a 2D array. Something more like a matrix that each cell will correspond to a physical location on the map. So we show the example right here. If you look at the simulator we have right now, this is Arvis. The simulator is in the background, although there's a little blue. There's some sort of simulator issues here, but don't worry. Genuinely, it still works. So this is our occupancy grid. The entire gray area, this gray square right here, you can see, is the occupancy grid. And this gray square is actually made of a lot of small cells together. If you zoom in, you can see that each of these small black dots is actually a cell. It's actually a single cell. So basically, by combining all the cells together, we have a representation of our environment. Now going back to the slides, we can see that each cell will denote the probability that a physical location is occupied. And that's the definition of a probability map, that we are basically saying that based on the input messages we get before, what's the chance of this particular location, the occupied cell, the occupancy grid cell is occupied. For our system in particular, 20% is the lower end cutoff, and 80% is the upper end cutoff. That means if there is like a probability above 80%, we say that, okay, it's basically 100% occupied. If it's an occupancy grid chance of lower than 20%, we say it's 0%. Static, also just reinforce what static means the object doesn't move. So for example, a building, a light pole, etc. So if there is like an old lady working in front of the driveway, we don't consider that in the occupancy grid, because that's a dynamic object. The old ladies keep moving as we keep track of the environments, and occupancy grid don't really handle that. There's another particular service that will handle that. There are some assumptions we make about the occupancy grid. we have a static environment, first of all. As mentioned before, we only deal with the world that is completely static. That means we don't care about the object that's moving, only care about the thing that's stationary. Second, independence of the cell. That means every cell within the occupancy grid doesn't impact each other. So if this cell has a chance to be occupied, it doesn't mean that the adjacent cell is occupied. Though in the real life situation, sometimes it does mean that. But in occupancy grid sense, in terms of mathematics sense, we say that if there's cells occupied, it doesn't rely on any other cell's information to produce the results. We also have to know vehicle's information at each step, such as where the vehicle is, etc. We also have to know the sensor model. That means we have to know what the type of sensor we're dealing with, the range of the sensor, the direction of the sensor. In our particular case, we use a LiDAR, which I will be able to actually show you guys in a simulation. So if we go to add a new topic and we go to, this is our LiDAR system. And you can see that this is our LiDAR point cloud. It looks a little hard to see, isn't it? There's all small dots. So let's actually make it a little bit bigger. It's more visible, slightly bigger. So right now the size is 0.1. Let's make it 0.0. Let's make it 0.1. And now it becomes a lot more visible how our environment looks like. In the simulation, it looks roughly like this. So there's like a buildings on the left and the right side, less smaller buildings. And it's basically identical to our LiDAR's outputs. Pretty interesting. It's 360. Slight downside is you can see how our occupancy grid actually don't reach to the area of the entire LiDAR, right? We'll talk about that in very, very soon. Why is that the case? Switching back to the presentation, why occupancy grid? Occupancy grid basically allows us to rely on a discrete timestamp, so a discrete input sequence to generate a solid image, understanding or guess, which way you want to call it, of an environment. And it's usually more efficient than the other solutions. And we can trust on it. That's the most important parts. Now we get into just a little bit of math before we hop into the entire workflow of occupancy grid. Don't worry, this should be relatively simpler than the other tech talks you should see. The reference will come from, a lot of the slides information come from EC 495. That will be our reference. If you are interested in where those slides are, they are in the autonomous team drive that's accessible for the core members, and you can look it up in details. Basically, the occupancy grid relies on a logit, which is log-out ratio. What are the advantages of log-out ratio? Log-out ratio is basically a function that allows you to process very, very high or very, very small probability to a reasonable logit number that you can deal with. This is a table of the logits of various probability from 0.01 to 0.99. You can see that the 50% chance you get a 0. And once you head down, you get a reasonable number to deal with. You head up, you also get a reasonable number to deal with. And even logit of a very, very small probability becomes like a number that's reasonable enough for us to process. So that's why we are going to use the logit-based formula to update the occupied probability of each cell. So what we rely on is the Bayesian logout update derivation. So for each cell, we have measurement updates, which is this is a little bit hard to understand at first, obviously, because this requires a lot more explanation. And that's why I say, if you're really interested, you should look into the drive for the more slides. This is part of the slides. But this formula essentially is saying the probability of the cell I is being occupied given the inputs from time 1 to time now, time equal t, which is now. And we're able to use the bias formula basically to reconstruct the probability into something that's more usable. We also will say we trust in Markov assumption. If you don't know what Markov assumption is, and if you know what memoryless property is, it's basically the same thing. The Markov assumption is that we can trust that our system don't rely on the previous inputs. So the new inputs doesn't rely on the previous inputs. It doesn't remember the history of inputs to produce a feasible outputs. So that's the definition, kind of a Markov, not exact definition, but kind of a definition for Markov assumption and memoryless property. Why is it particularly making our this is the reason why occupancy grid is kind of the most popular options, because this particular type of algorithm updates function will allow us to get a really, really good guess on the occupied chance of each cell when compared to other options available. And obviously, we can process further with this particular algorithm. Sorry, it's missing up a bit. There we go, mapping. So when it comes to the bias log odds update derivation, it's just I'm not gonna spend too much time on the derivation. I feel like this is just like math that you can't grasp immediately. That's also kind of why, again, recommend if you are interested, go read the slides on the drive. But basically, using bias rules, we're able to process these informations, and at the end, we will be able to get to calculate 1 minus p probability of m minus occupy over from input 1 to t, given input from 1 to t, right? And combine this, we get a logit ratio. If you look at this formula, if we go back, this actually is the logit function, probability of p over 1 minus p, log of p over 1 minus p. This is the logit ratio we have for the probability of cell I is occupied given input from 1 to t. Simplify further, we'll be able to get into some stage like this. And interesting enough, you can actually break them down into their own logit formula as well. You can see that this is the logit of probability of the cell Mi is occupied given by the input at time t. This is the inverse probability of the Mi being occupied itself. And this is the probability of Mi is occupied given the inputs from 1 to t minus 1. And remember, we're in a discrete system, so which means that time is not a continuous value. Time happens whenever the inputs happens. So at the end, we'll get taking the log yields, we'll get the logits of probability of Mi is occupied given the input from 1 to t, become the combination of logits that you could get from either the previous states or the new input information. So that's about the math. Relatively simpler, I would say. If you're really, really interested, I highly recommend you to check out the slides that was available. If you're interested in this thing like autonomous vehicle, like if you're just really interested into it, I also highly recommend taking the course EC 495, a really great course, I believe. And from this point forward, we start talking a bit about the pipelines. Like, what do we do? Now, after the math, what's the entire pipeline we go through? How do we, start from preparing? We go to maybe how do we start updating the state and how do we use it? So in terms of preparing, we first introduce cube crop is to eliminate the data collected from LiDAR that exceed the range that we require for our computation. We crop out all the points outside of the cube that we define in the code. So if you look at the simulation, right, you see how this is like a square. It's because we actively decided to say, hey, we don't want the information outside of the square. Obviously, we can define square to be like a different shape and stuff. There are parameters that allows us to do it, different sizes. But the main idea is that if we consider every single point that LiDAR can reach, first of all, when they pass a certain range, LiDAR becomes a little bit inconsistent. Second, it's not necessary data. It's way too much of the data we have to process. It's not necessary. It's so needed. And with the information within this particular square, it's more than enough for us to determine like what's going to happen next, to determine the path we're taking and determine the obstacle that's like closest to us, that's relevant to us. So going back to the presentation, we'll be able to see that cube crop, we're able to reduce the computation power needed to compute occupancy grid so we can maintain a relatively higher frame rate of updating. The next step we do is voxelizing point cloud. We define a size of a leaf, so usually minimum of 0.1 meter. And we basically say we filter the point cloud by generating the average point within each leaf. So look at this image to the bottom right. We basically turn this point cloud of an airplane into Legos. Or if you ever play Minecraft, it's like a Minecraft airplane now. It basically also helps us reduce the computational power further since there's less point to process now, but it also stays consistent enough for our purposes. It also eliminates some outliers and in some cases produce some sort of basic safety distance from the actual object itself. We can also look at, there's also one more processing we have to done is segmentation ground. I believe this is the part that's relatively more magical to us. We basically utilize the wave library produced by Autonomous. Thank you, Autonomous. They basically provided this library for us for free, and we're able to remove the points that represent ground and roads in our LiDAR system. It helps us to construct an accurate occupancy grid. One of the parameters that we're passing is the distance threshold, indicating the minimum distance above the ground for a point to be valid, so we can consider it in our future calculation. We also remove outliers for any point that doesn't have enough neighbors within a certain radius. We determine its outlier and remove it from the cloud. So that was it for the pre-processing. Now we're going to head into the pipeline update states. What do we do when we have all this information now processed? What do we do with it? Now in the update states, there are two main states that we keep track of. One is the occupancy grid itself. We update each cell using the Bayesian logout update derivation as shown before. And the second thing we keep track of is actually the tracked objects. The occupancy grid should and only should worry about the static objects. I will highlight this actually. Should and only should worry about the static objects. And thus, we should also keep track of a dynamic object and remove corresponding cell that is occupied by the dynamic object from the grid. So this helps us basically say if there is a passenger or there's like a someone on the sidewalk, we won't be basically tracking them because they're moving constantly. We're assuming, again, back to the main assumption, everything within occupancy grid that we know is a static object. It doesn't move. And for occupancy grid updates, it's just a little bit of miscellaneous in more detail what it does. If it's a first frame, we generate a brand new occupancy grid from the filter point cloud. If it's not the first frame, we pass the transform to the current time and the previous time into the occupancy grid generator to update. We use logout update to update the probability that the cell is occupied, and then for every cell within the map, we update their possibility using the logit function as mentioned before. So we increase the probability for detected obstacles, or decrease if the obstacle is no longer detected. Transform to a new map references is also pretty important. And if the old point is within the new point's map bound, append updated probability to it. It makes sure that it does not exceed the maximum or minimum allowed probability though. So if it wants to hit the gap, basically the 0% and 1%, it won't proceed forward. So that's basically a bit of a great update. It's a little bit more technical, a little bit more hard to understand over here. That's totally understandable. But it's not perhaps the most important part you ought to know about occupancy grid, because right now the most important part, I believe, comes into the usage of the pipeline. What do we do with this? Like now we have, let's say, sorry?
Oh, sorry. I just had a quick question.
Yeah.
I guess it might be a two-part, but it's kind of coupled a little bit. So like when you get the LiDAR frames in real time, how do you know, like, do you average them over like a couple of frames in order to tell if something is if an object is static, or like like if you have a parked car, do you consider that
part is object? That part is actually handled by the perception. So perception basically has a topic publishing all the dynamic object they track in the camera or other sensor system as well.
Sure.
And basically we listen to it and we get a track object, and now eliminate the corresponding cell within the occupancy grid that's tracked object, right? Because even though like the occupancy grid itself is still going to see the dynamic object as a stationary object. So our task is say, now we know where the dynamic objects are, let's go back to occupancy grid and remove them. So we can make sure that our grid only contains the stationary objects. That was the goal. Yeah, good question. Love that. So let's talk a little bit about the usage now. What do we do with this? Now we have this great map. Wow, we know the environment, at least the static environment around us. What do we do with it? Okay, in the ideal world, what do we do with it? There are two things mainly we currently working on right now, actually. One thing we do is we calculate the longitudinal distance. In other words, how far down the trajectory of the lane will we encounter an obstacle. The second thing we consider is the lateral shift, which is how much maybe to the left and right do we have to move to avoid the obstacle. A reminder is that we are not allowed to move into the opposite traffic, which is usually against the traffic rule. Perhaps will cause an accident, then endanger the drivers. And you're also not allowed to move off the lanelets. That means you literally are driving on the sidewalks. You could potentially damage pedestrians, which is very dangerous. And I understand this might be a little bit hard to visualize at first, so don't worry. Very soon we have some visual example where you can see how this turns out. So levels of computing that we basically do to achieve these are, first we have the functions to retrieve the desired occupancy cell based on the coordinates the current lane that you're on, adjacent lanelets, and you also detect obstacle in the lanelet givens between the maximum detection range and the current vehicle location. I know this part is also probably confusing. That's why we have examples coming up telling you what this exactly is. And once we found, we now retrieve longitudinal distance and lateral shift. And there's a special case that the obstacle might expand beyond the current lane, right? So here comes the example. This is a random Google Earth image I pull off internet. I don't even know where this lane is, being honest with you. But imagine that this is our situation, right? The green is our vehicle. In front of us, this is the lane we're in, right? And basically what happened is there is an obstacle in front of us. Oh no, occupancy grid, let's say, detected all the way to the end of the yellow boundary. So this end is right here, is where the boundary ends, is where the occupancy grid's radius detection ends. And we say, oh no, it's an obstacle. What do we do? Well, going back to this, what's the longitudinal distance? It's basically from the vehicle's location right here, all the way tracking up to the obstacle, the distance from following the center trajectory lane all the way to the obstacle, how far it is. Okay, now we have that. What's the lateral shift we have to make? So how far do the vehicle has to move to the left or right to avoid this? Well, we can see that the lateral distance actually like right here is about this size. We can move to the left to avoid it. And it has to be left. We can move to here. It have to be left. Why cannot be right? If we go into the right, we are literally driving on people's sidewalks. That would be dangerous, not recommended, and should not be done. So in this case, the lateral shift will be to the left by enough shift that's such that we will be able to avoid the obstacle. And if we take a look at it from a grid standpoint, like how the grid looks like, we also have some sort of grid looks like this. So this is basically how the grid looks roughly like, similar to this situation, except that now there's an obstacle. So let's say the cells right here, for example, are being occupied by red, right? They are the obstacles in the middle world that we see on our occupancy grid. And to reinforce again, what we do is we say this distance tracking down all the way to here is our longitudinal distance. And the distance to the left, how much we have to move to the left to avoid it, let's say right here, is our lateral shift to avoid the obstacle from colliding into our vehicle. And I got a few special cases that I want to ask, maybe help you guys understand how it works. So let's say we have this. Does anyone want to try to answer what would likely be the longitudinal distance and lateral shift in this case? Anyone?
The shift? You're asking what
Yeah.
the shift that would be like half a lane to the left?
Yeah? So like right here?
Yeah, like there.
Yeah. What about longitudinal distance?
I don't know, like 5 meters or something.
Yeah. I mean, around there. It's pretty much similar to this one, except now you move slightly to the left instead of completely to the left lane. So that will help us determine how much to the left we have to move. Maybe the obstacle is really small. We don't even have to move away from our current lane. That'll be the ideal case. What about in this case? The obstacle is on someone else's rooftop. What's the longitudinal distance that will shift in this case? Like this obstacle is completely off the road. You just see this random sign, stop sign on other people's rooftop.
You probably wouldn't shift at all, right?
Correct. The longitudinal distance is infinity or to the end of the completely. Usually we just denote as infinity. It's basically saying there is no obstacle on the lane, and there's also you don't have to move left and right at all. So yay, you can just proceed forward. Lovely. All right. Move this back. What about the next case? Suppose the obstacle is right here in the lane next to us. What's our longitudinal distance and lateral shift? Take a guess. Like any guess would be a great guess. Come on.
it's infinity again because like it's not in our path and like there's no lateral
Yes.
shift.
Perfect. That's absolutely correct. And the very last case, what happened here? Let's just say this obstacle is so big that it start blocking kind of both lanes together. Anyone want to take a guess? For what's the longitudinal distance and lateral shift?
Maybe the lateral shift is like infinity? I don't know.
The lateral shift is likely actually to be an infinity if this thing is unpassable. But if the obstacle is just a little bit to the left, to the right, where there's a little bit more space here, we might be allowed to say, hey, move this much to the left, like completely to the opposite lane, the other lane, and avoid this. Especially in this situation where lanelet doesn't really have a defined direction of traveling, we may be able to just shift this way and avoid it. It won't be against the traffic law as well. But in the longitudinal distance, in this case in particular, is also starting from here and hit the obstacle. It won't change. It won't be infinity. It will give you a specific amount, but it will be identical basically to say if the obstacle is right in the middle of the road. Cool. So that's actually the majority of the presentation about occupancy grid. Thank you for listening. Also, I have to give a lot of credit to my group members who's working hard. Thanks to them, occupancy grid has steadily improving. But yeah, right now we're in our QA time. Does anyone have any questions about the slide we presented? Any question? Feel free to ask.
Could I ask a question?
Oh yeah, go ahead.
So yeah, in the beginning you were talking about how each cell you have like a probability. So you said if it's under 20%, you say there's nothing there. If it's above 80%, you say yeah, there's something there. What happens if it's in between? What does occupancy grid do then?
We say it's undetermined. Basically, these cells are likely to have like you basically have you have to be above 80% for us to basically be saying. You see those black dots? All these black dots are 80% plus.
Okay, so you can't pass that.
Yeah. So if you don't pass the 80% threshold, we basically say that it's like it's maybe an obstacle, but we're not gonna pass it to you. It might be like a noise or something.
I see. So should we like be concerned if it's like we don't know? Do we just continue on? Like we just say, okay, we don't know.
Likely, yeah. Likely, what happened is if it's actually an obstacle and you're close enough to it, such that the lidar give you a good enough sensing results, it's gonna be like a good detection. Usually above 80% or around there. Like if you look at, let's say if I drive the car right here, right? Let's see if I can drive the car. Okay, let's drive the car. There you go, driving the car. You see how these small dots are actually just like the poles. Okay,
yeah.
the simulator is a little bit buggy, but you can actually see that these poles they're actually just like those wires right next to. That's why the detection is a little bit like a foggy, because this simulation see those wires fence and see like, oh, detection is kind of hard because they are really thin, right? But the buildings next to you see those very solid objects.
Yeah.
Even far away, they are pretty good detection.
I see. Okay.
And we can even like detect all these small like buildings, the front of small buildings over here as well. And it gives us a good idea how our environment looks like. And in particular, in this case, our cells like actually has like a really not refined. Like you can see the cells are huge actually, if you think about it. Cells are pretty big. We can tune it to smaller that it will generate almost like identical image to the LiDAR that you see right now, except it's a probability map and it's more accurate than the LiDAR than everything together. Just a point cloud with no order.
I see.
Yeah. Good question. Love that.
Yeah.
Anyone else? Feel free to ask any questions. I'm happy to answer any of them. If you're too shy to talk, you can also raise your hand and I will pick you out.
So how do we make sure that the lateral deviation that we're giving will not cause us to violate traffic laws?
So basically, a part of the thing what we do is we check the lanes that we're currently on, and we check the adjacent lane, and all the way until the lanes that's not in the same traffic directions. So we only consider lateral shift to the lane of the same traveling direction, not outside the lane, not to the lane, extend toward the lane of like opposing traffic. If that happens, we say that, oh, there's no space left. So basically, maybe lateral shift to the right is impossible in this case because it goes off the lane. Or the lateral shift to left is impossible in this case. It's go against the traffic law. The lambda model we have tells us the direction of the lane that it travels in, which is really helpful for us to determine if we're allowed to go on the other lane at all. If it's allowed, obviously we say, okay, if it's allowed, we always want to go to left. So in this case, let's say in this case, let's say the left traffic is allowed, it's in the same direction. We say, okay, perfect, we're just gonna move to the left. You know, the lateral shift is gonna be like right here. We're allowed to move to the left to avoid this. But let's say it's in the opposite traffic. We basically say it's impossible to get past this obstacle without violating traffic rules. When we, unfortunately, in that case, we have to return no. We are blocked here. Yeah. Does that answer it? Right. Anyway, any other questions? Any questions? Any questions you want to ask about occupancy grid? Maybe how it works and stuff.
So then that means occupancy grid depends on HG maps, perception, and
LiDAR.
LiDAR, yeah.
Yep. We depends on that. We're basically refining their data to become something more reliable instead of just a random point cloud, you see.
Mm-hmm.
Any questions? Any other questions?
Yeah, I guess one more thing. Like, I didn't really catch like why you guys were using the log odd stuff.
Oh yeah, this is a more of a logouts is just a really useful function for us to update the probability of a cell being occupied. This part is relatively more of a complex math that particular like you won't touch with this until even the like, you have to fast on statistic background for even to understand what this means. And then later on, you have to perhaps in later years you also take some courses that actually start using this, robotics courses in particular. But if you want to know more detail about this, I highly recommend you to visit this particular drive. Under the software pathfinding occupancy grid, there are particular. Actually, I might be able to show you right here. There are particular 4 different PowerPoints, all from ECE 495, that detail you describe the way we do the occupancy grid here. And also, I have to give a credit to Autonomous. A large percentage of our code base is basically from Autonomous's occupancy grid system. They have implemented a very useful system. We understand. We learn the system, understood the system. We just reuse it, and we try to perform actually improve the actual features on it. That's mainly our task. But that's it's still pretty interesting. I would say it's a pretty difficult task to do. If any of you are really interested into the occupancy grid and stuff and how the math works behind them, these 4 slides are great. They basically summarize most of the information you would know. There are some others from like mechatronic classes, but those are similar content except a little bit harder to understand. Yeah. Would that be solving your question?
Yeah, I guess so. Like from a high level, I guess. So it just makes like updating like the state easier. Like
Yeah.
What's the state?
It makes the updating the states more accurate and easier, and it also allows us to rely a little bit on the previous state to update the current state, which makes the processing really efficient.
Gotcha.
It's similar to dynamic programming's idea, but obviously that's only similar, not exactly identical.
Hey,
Yeah.
I was wondering how we can carry out the maneuvers when we're avoiding obstacles. Like, is the purpose of the occupancy grid to just calculate the longitudinal and lateral deviations?
Good question. Maneuver is not handled by us. We are basically the supplier information for the local planner, who basically plan how do we do the maneuvers. Like for example, in this case, you kind of have to, go to the left, right, and then go back
and
to
you gotta
here.
remember to come back.
Yeah, this part is not handled by us, but the team that handles it basically eats our information about the occupancy information and uses it.
I see, I see. Because I was just wondering what will happen in this case when the known lane or the traffic law of this particular region allows you to step to the left lane to dodge it. However,
Yeah.
another incoming traffic was just turning around the corner. I was just thinking about how you guys generalize the process of avoiding obstacles while not having collisions.
True. This issue is not particular part of occupancy grid, unfortunately. I would love to answer if I could, but it's
I can
more handled
explain.
by. Yeah.
That's
Oh yeah.
it's
Cool.
really part of local planning and control. So in occupancy grid, we use logit function. Similarly, in local planning and control, we use something like a sigmoid function. So if you know sigmoid function, so basically that helps us to take this lateral shift and longitudinal distance provided by occupancy grid and then do a lane change maneuver.
Oh, yes. Yeah, I remember you talking about it.
Exactly.
However, yeah, Kushan, you were using these functions as the trajectory for our vehicle. However, I remember we had this conversation too. Our current maneuvering process is not generalized. Like we will just say like execute the maneuver, and I guess the vehicle doesn't do much else. Like it doesn't perform the standard surveying when you're performing this maneuver. So I was just wondering if when you were you were in the middle of this maneuver, how would you still be uh, like how did you design the process such that you're still detecting if more obstacles are in the maneuver
Oh,
lane?
so I mean, for each, like as we are following the lane, all the obstacle information will be passed on from occupancy, from behavioral planner and occupancy grid team. So I mean, we just do trajectory generation and following of spline. We don't consider which obstacle to go around and which to not. Like if there's an obstacle in a way, we will find the trajectory across it. And then occupancy grid decides to pass us whether we have to move to left part or the right part of the lane. But yeah, it's our part is mostly like you have an obstacle, you try to overcome, go or find splines around it. That's the way it works.
Okay, so I believe what's going on here is like it's not you plan a maneuver and then you execute the maneuver. The maneuver is being continuously replanned at every single time step,
Yeah.
right?
Yeah.
So
So it's basically like a convergent solution, like a optimal control problem that we have to solve at every point. So your MPC, I mean, model predictor controller tries to converge to a point which satisfies those constraints.
Okay, that makes more sense. Yeah.
Yeah.
Ideally, of course, our algorithm would have to recalculate the route the vehicle is taking at every cycle, if you will. And I was just wondering how do you keep this memory of, like after surpassing the obstacle, you have to go back to the current lane. Is that just a part of the constraint?
Oh, yeah. So, I mean, this is again, our solution is more of a combo of L sigmoid and the OCP. So as soon as you do a lane change, the MPC will try to bring back the vehicle to the current lane. So you pass your source and destination in RVIS. Just assume that you pass some source and destination point. So your MPC will try to keep your vehicle on the lane. Like it's a following thing. It's a path following technique. But this LC sigmoid will drive around the obstacle. So as soon as you drive around the obstacle, the MPC will again try to retrace the vehicle to its original path.
Oh, okay. All right. So your constraint is saying that since we calculated the route if there were no obstacle and you feed it to the NPC, and this compartment like the like I guess the part of the local planner that goes around the obstacles, they will tell the NPCs, say, hey, we currently have an exception in our rule, and we would like to, make an addition to your to the optimal spline. And then the NPC will keep these exceptions in mind and always tries to go back to its previous lane. Is that it?
Exactly. Yeah, that's it.
Cool. Okay, thank you.
Lovely. Thank God you're here. Yeah, that wouldn't be a question for me. Thank God.
Yeah, I did have a question for you. So, are there
Oh.
any edge cases that you have come across with the current implementation?
Edge cases?
Yeah,
Like the only
somewhere
edge
where.
case that we think about is like, what if like we only check the current lane, right? What if like
Hmm.
the obstacle is kind of like here? So part of the obstacle is expand beyond the current lane, right? So what we do right now is if we find an obstacle expand beyond current lane, we also run the algorithm on the not exactly on the adjacent lane, but start from the point of contact and expand on any adjacent point that's also occupied
Oh,
to
I see.
generate a full connected object that you're going to see, and then use these points to determine the lateral shift, the longitudinal distance you have to shift. Because in this case, you still want to go to the left. It's still doable. Right? It's definitely not doable. Let's say it's like that. Oh, sorry, wrong image. Let's say it looks like that, right? The right lane is definitely not doable, but left lane still has enough space. But we cannot just give you the left boundary, which is like as much as we detect, because they expand beyond the lane. So we have to give you somewhere like around right here, and then now we maneuver through it.
Oh,
Like
okay.
beside it. That was the edge case.
I think there is also another one that could pop up depending on how we implement the bounding box.
Yeah.
Which is like, I think it was Rowan that mentioned this, but if we have, say, a small obstacle on the left side of the road and a small obstacle on the right side, but there's enough space in the middle to pass by, the bounding box we make could mistaken these two obstacles as one.
Not likely though. So are you saying like this
Yeah,
case?
something like that.
This case,
Yeah,
this
just like
particular
depending
case.
on how we write the code.
In this case, we kind of say that it's being the two cells basically saying like we've considered them as the same obstacle within the lane. That's kind of what we do. But realistically, ideally, even in this type of case, like if possible for maneuver, you should try to do that though. Because if there's like two obstacles on the lane that's big enough to be detected, likely they're pretty big and pretty dangerous to suddenly traverse between them. It'll be probably more ideal to shift if possible. But yeah, there's also like edge cases being thinking of. All right. Cool. Any other questions? Are everyone satisfied with my terrible drawing skill and presentation skill?
Oh, thank you, Justin, for the great presentation.
Well, thank you for that compliment. That's amazing.
Okay, thanks guys for coming. We'll see you all next, I guess in 2 weeks, I guess, for the next all hands. But yeah, thanks for coming.
Yeah, thanks for the presentation.
Thank you.
Thank you.
It was a great talk. Thanks.
Thank you, guys.